do some smart calculations for you. You do not need to put this in your notes. Don't put this in your notes. But let's work together to fill out this table. So here we have 25 different bacteria. And we're going to show the growth of the 25 bacteria, assuming that the entire population doubles every hour. So at time 0, we would be at what? 0. That's an obvious one. 0. But we're starting with 25 bacteria. So we're starting with 25. Now if it doubles, I think we can all easily double that. What's 25 doubled? 50. Double again. 100. Double again. Double again. Double again. And again. 1600. Good. All right. So let's come up with an algebraic expression that represents the population after n hours. Like if we had to write the rule for that table.
N squared. Yeah. No. N times 2.
2x. I'm hearing 2x. 2 times x.
Yeah.
All right. Well, what if we make time be our x and population be our y?
Y equals.
Guys are thinking. Keep thinking.
Oh, it's like 2 of the 2 times the previous hour plus the now hour. So like if you did like 25, so 25 times 2 is 50.
Yeah.
50 is 100. You could also do 50 times 2 is 100 plus 100 equals 200. And then that just keeps going on and on.
So we're all doing that. We're timesing by 2 each time, right?
Yeah.
Okay. Are my x's consistent? What's happening there?
Yeah.
Plus 1, plus 1, plus 1, and so forth. Okay. If this was a linear equation, what would be the slope? Slope is y over x. It would be 2. Okay? But this is not going to be an example of a linear because it's not plus 2 plus 2 plus 2 each time. It's times 2 times 2 times 2 each time. If it was plus 2, then it would be linear. So it's not linear, so we can't be thinking 2 times x. What else?
Divided.
All right, let's take some cue words from what we wrote for our description of our title of our section. It was exponential. What word is in the word exponential? Exponent. What does an exponent look like?
The little superscript.
Yep, the superscript on a number. So if I were to, let's say, do x, sorry, to a power, like if I did, let's say we did 2 to x. I feel like I'm losing my voice here in a second. What's 2 to the 0 power? It's 1, isn't it? What's 2 to the first power?
2.
What's 2 to the third, second power? 4. 2 to the third. Wow, I'm really losing my voice right now. This is so weird. 2 to the fourth? 16. 2 to the fifth?
32.
32. 2 to the sixth?
64.
Okay, so is there any way we can make a connection with that?
Sure. I don't know how, but I'm sure we can.
Well, 2 to the first, or 2 to the 0 we said was what? 1. What do I need to multiply 1 by to get to 25? 25. So let's just play around with this for a second. So I'm going to put 25 times 2 to the x. What's 2 to the first? 2 to the first is 2 times 25. Is that 50? Will it work with 3? 2 to the third is 8. Is 8 times 25 200? 2 to the 4th we said was 16. Is 16 times 25 400? Yeah, it is. Okay, so let's think about this. What do you think would change with our expression here, or equation, let's make it equal to y, if I tripled the bacteria growth?
Would just be in parentheses.
What did we do here? We doubled. What number represents double? 2. So it would be 3 to the x. What if I quadrupled? 4 to the x. All right, so what I want you to do, calculator in hand, go to your y equals screen. Go to y equals, and I want you to type in y equals 25 times 2 to the x power.
How do you do to the
You're going to have to use that caret and then put the x up as the exponent.
What do you press after that?
Huh?
What do you press after that?
After what?
You type it in, you press enter.
Oh, hit graph.
graph?
All right, so let me get mine typed in
Bro,
here.
what world? Where did it go? I can't even see it.
Oh, I'm still on my shade it. I don't want shade it. All right, so are you getting, you should not be getting the shaded part unless you still have the shading from the last time we did the inequalities. Huh?
What?
Shade on a regular calculator, is that?
Yeah, didn't we do it when we did our inequalities?
I still don't know how to shade.
I feel like we did.
No, mine's a different. I was in here for negative 1.
Rookie mistake, Haley.
I know, sorry.
Let me get rid of this. There we go. All right, so we got our graph. Is our graph linear?
No.
No.
It's not a line, is it? Is it a function?
Yes.
Yes, it passes the vertical line test, right? Okay, let's hit the trace button and make sure our numbers that we had did work out. So let's trace 0, hit enter. Did we get 25?
Yep.
1, enter. We get 50. 2, enter. 100. 3, enter, and so forth. Good. Okay. So, someone describe to me what an exponential graph looks like. Will this ever hook back up like a parabola?
No.
It's not, right? Guys, quietly.
That was crazy.
Erica and Jason, obviously. Will this line ever go below the x-axis?
No.
Yes.
Yes.
What does this line represent?
It will never go.
This line represents right now our bacteria growth, right?
Oh, so it has to start at 0.
This time,
We can have negative growth
right.
You can't have that.
or decay, as I like to call it.
Negative growth and negative decay.
Negative growth equals negative decay.
Let me zoom out.
Regular
What?
decay.
Yes.
Don't get
All right, I just zoomed out.
Holy crap.
This means you probably have a stat plot on. Your stat plot's off. All right, let me change my window here. Are we ever going to have negative time?
No.
No. So should I have an x minimum value of a negative number?
No.
No. So I should be starting my x at what time? 0. Okay.
So it's just going to be a Y.
How much time do we want to do?
Oh,
50 years?
50 years.
Okay. Y minimum. Are we ever going to have a negative amount of bacteria?
No.
No. Let's go 0.
Anything
Y
else?
max.
100. 500.
Well, think about on our table. What was the highest we had on our Y table
Oh,
there?
1600.
1600. Let's go 2000. See what that looks like. There we go.
Start curving backwards.
Guys, what is going on? So, This is a little bit more representative of what's happening, right? Bacteria starting at 25 at 0 time, and then 1 or whatever the scale is, I'm not quite sure what the scale is our bacteria. So it's growing exponentially. We said that it's never going to go below 0 because there's no way to get less than 0 bacteria if we're starting with 25 and it's growing, right? So that's never going to go below 0 and it's going to be going up. What would happen to our graph if I tripled it? Would it get steeper or less steep?
Wait, like you mean like that
It would get
Like if I made it a 3 instead of a 2 and tripled
It would
each
get
time.
steeper.
It would get steeper because it would get higher quicker,
Yeah.
right? Does that make sense? Which if you wrap your brain around money, it's better to have a higher interest rate because that's going to get...
You make more money faster.
Right, so let's quickly come up with something for money. Go back to your y equals screen. How much money do we want to start off with?
$7.
$1,000?
Yeah,
$7.
Maybe we should let's do a smaller because that's going to be pretty crazy. Let's start with $10. Sorry, I'm starting with $10. You only get $10 from me. If it were to double each year, so 2 to the x, let's see what that looks like. Graph it.
Looks like almost the same.
So if I go to trace, after 1 year, my $10, whoop, oh, come back, trace. After 1 year, my $10 is at 20. Is that pretty good? Going from 10 to 20?
Oh yeah, no, mine's here.
Sure.
Wait, can you show how to make it like that again?
Go back to your window. That's the window I used.
Where do you? I don't know how am I doing?
It's right next to the y equals button. It says window.
Wait, what?
And then
So I have 0, 50, and then 0, and then 2,000.
wait, why do you? Okay, whatever. I didn't change it.
Just because I want to see the first quadrant. I don't really care about the other quadrants.
Yeah, I'd say.
Yeah, now my number is when I plug it in, it doesn't repeat. Oh, thank you. Like with Andy's, like you know how.
When you go to trace it.
Yeah. Oh, I got it. I got it. Thank you.
Don't worry about this other. Just get the 0 and the 50. Okay. If we go to 3 years, I now have how much money? 80. Guys, please stay focused. Phones should not be out. 4 years gets me to 160. So from 0 to 4 years, if I was doubling my $10 each year, it's got some slow growth. I mean, that's not bad, doubling your money each year. But why would it be beneficial to leave money in an account for a much longer spread of time? Because once it reaches like this point right here, it's going to start skyrocketing, right? So after, let's say, 10 years, how much is that $10 going to be worth?
Wait, after how many?
Holy
10.
cow.
What?
$10,240 after 10 years.
That's not a realistic interest rate.
No, you're not going to find it.
Why didn't I put 10?
Because that would be like a 200% interest rate if you doubled something, which is insane.
It's a special.
If you find one, then you let me know what it is when you find it, okay? After 50 years,
Wow.
it's scientific
You
notation.
didn't put in E's, you're making that much money.
That's how much money, so what is that? So 1, 1, 2, 5, 9, 16 spaces. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16.
That is a lot of.
How much money is that?
After 50 years?
Wow, that's
That's more than
Is that enough money for you to retire and do whatever you want for the rest of your life?
And everybody else.
All right, let's go back to our notes.
Wait, divide that by a billion. What would you get?
Divide that by a billion,
Yeah.
so that we would take out 100,000 million billion, so it would just be that number, right?
I'd give each kid in Africa that much amount of money.
Yeah?
Yeah.
And you keep the
And then
billion for
everybody
yourself?
would be like,
All right, so now we see what an exponential function looks like graphically, and the purpose of exponential functions. Everything grows exponentially, we hope. Sometimes things decay, which isn't as good if we're talking about money. We don't want our money to decay. So what is an exponential expression? Well, it's an expression that has a variable in the exponent, and the base is going to be some type of fixed number. Okay? So if someone gave you an opportunity of saying, I'm going to give you $1 each day and double it, or I'm going to give you $1 million, which option would you pick?
dollar.
And double it each day for the rest of your life would be your best bet, instead of just getting $1 million, because then you'll be really rich at the end of your life. So,
I'd rather have the money.
but then, do you want the money now or later?
Time I die.
How about they said until you're 50? Until you're 50. Double your dollar. All right, another vocabulary word that's going to pop up is the word multiplier.
Multiplier.
Yes, so if you are asked to find the multiplier of an exponential expression, it's going to be the base of an exponential expression. So in our example that we've had, for the bacteria, we had, let's say, 25 times 2 to the x. That would be an exponential expression because the x is in my exponent. Now let's quickly think. Would the multiplier be the 2 or would it be the 50? The 2. Why?
Because
the base.
Order of operations tells us we're going to do what first? Exponents before the multiplication. Bless you. So don't do PEMDAS backwards and multiply that and then say my multiplier is 50. It's not. Your multiplier is 2 in this problem. Got it? All right. When we're talking about a growth rate, we're going to be thinking about 1 plus whatever that rate is that you are growing by. And the reason why you need to have the 1 plus, because if rate's usually given to you as percents, right? Okay, so if I were going to exponentially grow by 5%, I'm not going to just be starting at 5%. I don't start at 0%. I start at 1% of the whole, and then I'm adding 5% each time. Does that make sense? Do I need to say that again?
Do we change it to a decimal?
Yeah, you're going to change that to a decimal. Yeah, this should be a decimal because your calculator is not going to be able to let you put it in as a percent. So this should be a decimal. Good question. So that's why it's 1 plus, because you're starting with 1% of your amount of money, your current principal, and then you're adding the interest rate onto it. You're not starting at 0 of nothing, though I guess it could be 0. All right, so if I gave you a rate of 5.5% growth, I want to find the multiplier for the rate. So I'm looking for that growth rate. So to find the growth rate, we're going to do 1 plus our r. What is 5.5% as a decimal?
0.055.
So 0.055. Remember, you just move your decimal over 2 places. So adding those together gets us 1.055 would be your multiplier. Yep, that's it. So I think like the first few problems in your textbook for homework are find the multiplier, and that's all you're going to do. You just need to decide whether it's growth or decay. For B, if my percent of growth is 0.74, it's going to be 1 plus what? 0.0074. Pay very close attention. This is where you guys are going to make really silly mistakes. You're not going to put enough zeros here for your 0.74%. Don't say 0.74% as a decimal is 0.74. That's 74%, which is way different than 0.74%. Okay, if your banker made that mistake and said that it was 0.74 instead of 0.0074, then you're going to be getting lots of money. That would be great for you, but bad for them. So adding those together gets us 1.0074. So that would be your multiplier. So when we turn these into exponential expressions, these would be the numbers that would have the x as the exponent. So it would be 1.0074 to the x power. It would be 1.055 to the x power. Okay? All right, let's get into some word problems. Feel free to write whatever it is you want to write. So we got the population in the United States in 1990. So that's an important number. Was 284,718,301. And that was in 1990. It was projected to grow at a rate of 8% per decade. So we got to remember the word decade there. It's not by years. Decade is 10 years, right?
So that'd be 3 decades to 2020.
Yes. So now we need to predict the population to the nearest 100,000s for the years 2020 and then 2050. So here's how we're going to set up our equation. Y equals. It's going to be our initial, I'm going to write it out first in words, our initial amount times, in this case, it's going to be our growth rate, which is our multiplier, to the x power. Guess I should have made my parentheses about the same. So at time 0, like when we did the bacteria, we were starting with 25 bacteria. So that's why it was 25 times 2, where 2 was the multiplier. Here we're starting out with how many people? 284 million. So it equals 718,301 times, what's going to be my growth rate?
0.08.
So the multiplier would be
1.0.
1.08, right? So if we need to write it out, 1 plus 0.08, which really is 1.08 to the x power. So there's our equation. So now we need to figure out what value we're going to put in for x for 2020, which would be, so 1990 to 2000 is 1, 2000 to 2010 is 2, and like Ben said, 2010 to 2020 would be 3. So this is where you're going to need your calculator. We're going to input 3 for x. Now your calculator will do order of operations for you. So if you just type it in as one string, that's probably your best bet. So 284,718,301 times 1.082, the third power, and we get a very large number, because we're talking large numbers and we're getting bigger. I'm going to write it up here. I'm getting 358,663,060.4. Put in my commas. So we now have gotten how many people? 358,663,060 people. If I were to round this to the nearest 100,000, what would that look like? Would I round the 358? No. What would the 663,000 round to? It would round to 700,000, right? I'll take either as an answer, but just know if you look in your textbook and at the answer and it's rounded, that's how. 2050 would give us x to be what? 5, because I have to go 2 more decades, right? No. 3 2020 to 2030, 30 to 40, 40, so it'd be 6, right? So what does that number go to? And what's nice on these calculators, if you hit second and the enter button, it brings back your previous entry, and then you can just go and change that 3 exponent to a 6. That's typing. Second and enter gets you to entry. So I'm getting 4, 5, 1, 8, 1, 2, 1, 6, 1.1. So 451 million and 800,000 if we were rounding that to the nearest hundred thousandths. Okay. All right, so that's an example of growth. What are some other things that grow? Okay, sure. I don't know if plants grow exponentially, because eventually they slow down in growth. Huh? Money grows, right? Usually, if you put them in like an interest rate, not on trees. What are some things that lose value over time? Like inflation? Like that type of idea?
I was thinking more of like value.
How about cars? When you drive a car off a car lot, brand new car, how much? It goes down a lot, right? Then hopefully at some point it becomes a classic, and then it might bring value back to it if it's an antique. What else loses value? Technology. Technology loses value really quickly.
And then it'll be valuable in 100 years, though.
Maybe.
No, it will be.
All right, so these are all examples of decay. We're almost there. Hang tough. So when we are talking about things losing value or things decaying, then they find that multiplier, otherwise known as the decay rate. You're going to do 1 minus your rate.
Same equation, except this is.
Yeah. Okay. So it's going to be a number less than 1 because you're losing value, right? So if we had the same percentages, but I just changed it to decay, what would be the multipliers? So think about what 100% minus 5.5% would be. Nope, 100% minus 5.5.
0.945.
Right, it'd be 94.5, which is what decimal 0.945, or 1 minus 0.055, which is 0.945. I have a coughing fit. I can feel it. What would it be for 0.74? 0.9926. So 0.9926, and we're getting that by doing 1 minus 0.0072 or 74. Okay. All right, let's do a problem yet, and then we'll be done.
So, multiplier is the same thing as the growth
Right.
rate?
Yeah, and the homework it's going to
Multipliers?
right. The homework's going to say find the multipliers. All right. Do we want to do caffeine or car?
Caffeine seems longer.
All right. So let's buy a car for $15,000. The value depreciates at a rate of about 8% per year. Predict the value of the car to the nearest cent after 4 and 7 years. So if we use the same idea, y is going to be equal to the initial amount. Are we growing or decaying? Decaying. So our decay rate to the x power. So my initial amount for the car is $15,000 times, what would be the decay rate if it's decaying 8% per year? 0.92. right? Because you have to take 100 minus 8%,
Yeah.
which would be 92%. If you can't think about that in your head, do 1 minus 0.08, which gets you 0.92 to the x power. What am I going to input for x for 4 years? 4. So let's plug in 4 into our calculator. So 15,000 times 0.92 to the 4th, $10,745.89. That's how much your car is worth after 4 years. How much is your car worth after 7 years?
Would our exponent be 7?
Yep, exponent would then be 7. 8,300. There's a lot of chatter, guys. I'm really already giving you guys 1 strike for choosing your own seats. Don't get 3.
Can we round it to 70? Okay.
Yeah, I would round that to 70. Okay? So you need to ask yourself, is it growing or is it decaying? The setup is the same, initial amount times your multiplier. You just need to decide, is your multiplier going to be a growth rate or a decay rate? Got it? All right, questions?
So not every time